Okay, one more minute to go. Awesome. Okay, good morning, everybody. I hope you can hear me. I think you can hear me. I'd like to welcome us all to this, the second of two webinars in joint partnership with the Water Resources Authority of Jamaica and the International Atomic Energy Agency. We had our first presentation yesterday with Christos Penos looking at drones and their application in hydrology. And today we'll be looking at Karst hydrology and specifically looking at the Rio Bueno sub-WMU, which is the focus of this particular project, which the WRA and the IAEA are jointly pursuing. I'd like to thank you all for being here. I do want to at least welcome two persons. First, I'd like to welcome the first WRA staff who are present. I'd like to welcome also Miss Natalie Pearson, who was a past employee of the WRA. And I want to give a special shout out to Miss Lee Ann Bledsoe from Western Kentucky University, Crawford Hydrology Lab, who is our joint partner with dye tracing. She's really helped a lot with all of the things we've done. Highly nice to see you. Glad to see you could join us. And our presenter today is Dr. Aurel. How do you pronounce your last name, Aurel?
Pershoiu.
Soy. From Romania. He is, let me pull up the introduction that was right here. Let me read it out. He's a senior research fellow at the Emil Rakovitia Institute of Speleology and University of Suceava in Romania. He has a PhD from the University of South Florida. And his research involves stable isotope geochemistry and paleoclimatology. And he is very well equipped and capable to speak to us today about Karst hydrology and isotope hydrology and the water resources on this particular project. So without further ado, I now turn over the virtual lecture to Dr. Aurel Persloy. The floor is yours, sir.
Yeah. Thank you, Geoffrey, for the nice introduction. Thank you, everybody, for being here. So I will be talking a bit about, I will have an introduction into stable isotope geochemistry, and then followed by a bit of discussion on Karst hydrology, some basic concepts. And then I will finish up with a few words on some ideas that could be pursued by the Water Authority in studying and using stable isotopes to study the hydrology of the cockpit karst area in the Rio Bueno region. So I will share my screen now. Let's see, play slideshow first, and then share screen. Okay. I guess this is it. So is it on the screen now?
Yes, we're seeing it well. We're seeing it fine.
Okay. So I just put tiny deltas in reference to the deltas that we are measuring in when we are dealing with stable isotopes, and on Karst hydrology with cockpit in parentheses, just to emphasize that most of the talk will deal with the karst rather than specifically with this case of the cockpit. So I would like to leave this to the end of the discussion, where so the main idea would be that to discuss on based on what I am presenting now, how to best use the stable isotopes in water in combination with other data and methods to study the hydrology of the region. So I just took this from Google Earth. It's from the Karst area in northern Jamaica. Okay, so let's see, how can I, okay. So this is a brief outline of my presentation. I will be focusing on the stabilized of geochemistry and then Karst hydrology with Karst, and these two will be together discussion on how to stabilize it, mostly by presenting several case studies and how can stabilizers be used in Karst hydrology. Okay, a bit of introduction. That's what I mostly do. So I work in caves and karst, and I use stable isotopes to study the dynamics of water from precipitation to the moment that oxygen and hydrogen in the water are being locked in speleothems or other cave deposits like ice deposits in caves, so that I can do paleoclimate reconstructions. Okay, my office and my other office, my field office with my colleagues in the field. Okay, so part one will be a general stabilized of geochemistry introduction. I will start from the beginning and then just quickly walk you through a bit of discussion on stable isotopes. So first, let's see about what are stable isotopes. I put these pictures of Democritus, who was the first to introduce the concept of atom, and then Nier, who built one of the first useful mass spectrometers that were used to study the ratios of stable isotopes. So going here, we are talking about isotopes, that is forms of the same element that have the same number of protons but a different number of neutrons. And you can see here for the hydrogen and for oxygen, the same number of protons in the case of hydrogen 1, and deuterium has a neutron. And for oxygen, we have the 8 neutrons and the 8 protons and the 8 neutrons. In the most abundant oxygen 16. And then we have oxygen 18 that has 8 protons and it has 10 neutrons. And these 2 neutrons here will increase the mass of oxygen 18 as compared to oxygen 16. And this is most probably the most important characteristic of these isotopes, is this higher mass that is important for our studying the isotopes and the ratios between the light and the heavy, with oxygen 16 and 18. And these differences in mass are translated into a difference in the potential energy. So if we are looking at the energy of a molecule that is composed of light or heavy isotopes, we will need an energy. This is called the energy that is required to dissociate the atoms. And this energy, it is higher in the case where we have the heavier isotopes involved. So here D denotes the deuterium, this one. So as you can see, the energy required to dissociate atoms that are composed of the heavy forms of an element, be it the hydrogen or oxygen, it is higher. You need more energy to dissociate these atoms. So this is what is happening is that we have a stronger binding energy for the heavy isotopes as compared to the light ones. And because they have this stronger bonding energy, you need more energy to dissociate them. And this is important when we are discussing the fractionation and how these different types of isotopes, light or heavy, are moving to the hydrological cycle. So this is actually the energy that is required. And this is one of the important messages I want to convey, is that we need more energy to dissociate a molecule with heavy atoms, like hydrogen 2 or oxygen 18, as compared with the light one. And I just put here a quick show. So we have the heavier atoms, oxygen 18, and then we have the light one, oxygen 16. I'm not sure, is my pointer visible on the screen? Can you see my pointer? Can you see my mouse moving?
Yes, we see it.
Okay, so there is a stronger energy involved between the heavy atoms as compared with the light ones. There is a weaker energy. So for instance, when you have the evaporation of the water, both molecules that have oxygen 18 and oxygen 16 are evaporating, But oxygen 16, the molecule, the isotopologue that involves the oxygen 16 evaporates more readily. So that means that in time, there is an enrichment of the vapor in the light-bearing molecule, whereas the remaining water will be enriched in the isotopologue with the heavy one. What is happening in the clouds is exactly the opposite. Oxygen 18 is preferentially removed. So not only oxygen 18, but also hydrogen 2 or deuterium. So that means that compared with the vapor, the precipitation will be enriched in the heavy isotope and depleted in the light one. So if we go further, yeah, we'll just skip. So if we start with the ocean, which by convention has a delta value of 0, and this delta value is how we measure, because if we want to measure the ratio of oxygen 18, the number of atoms, oxygen 18 compared to oxygen 16, this is a very small number. So it is difficult to work with. So then by convention, it is measured in a sample and is reported to a standard. And this standard is the ocean water, and this by convention has a value of 0. So all the deltas are measured, all the delta 18 values or delta 2H values are measured relative to the ocean water, which has a value of 0. So if you see values that are negative, like here, that means that these values are depleted in the heavy isotope. And if you see positive values, like +3, 4, 5, that means that they are enriched in the heavy isotopes. So what is happening here, if you look at the evaporation, because of the fact that the lighter isotope, oxygen 16 and hydrogen 1, are evaporating more easily, that means that the vapor will be depleted in the heavy isotopes. So it will have a value of about, let's say, -12. This is just for example. Now, when it comes to precipitation, because oxygen 18, the heavier one, will be preferentially incorporated into precipitation, where it's better, there is a stronger link between the water molecules in liquid phase than compared to the vapor phase. That means that the water that is coming from this rain will be enriched in the heavy isotope. So the values will grow from -12 towards -3. The remaining water, the remaining vapor will be even more depleted. So instead of like -12, it will be -15. So the next rain that will come out will have an even lower value, -11 compared to -3, leaving the vapor further depleted, -17 and so on. So this process is continuing until you stop the rain, or basically all the vapor in the cloud is converted to rain, to liquid water precipitation, and falls to the ground. So this is just a simplification, just to show what is actually happening, because you have some other processes that are complicating the picture, like you can have re-evaporation from the ground, and this will replenish the vapor in the air, changing its isotopic composition and so on. But this is a basic scheme that actually shows what is happening with the delta O18, what is happening with the oxygen and hydrogen in the water as it leaves the ocean and is moving further to the land. Okay, just is complicated a bit, so you see the same scheme showing that the vapor, and it shows the potential complication of this by evaporation and so on. The basic idea is that because of all these processes of evaporation and precipitation, there are several effects, so-called effects, that are affecting the stable isotope composition of precipitation at a given point. One would be the so-called continental effect. That means that the further we go inside the continent, that the more depleted the vapor and the precipitation will be in the heavy isotopes, in the oxygen 60, oxygen 18 and hydrogen 2. And then we have an altitude effect, which is the same, because the higher we go, the stronger the condensation, the more precipitation we have. And again, the more precipitation we have, regardless of what is causing that more precipitation, we will have a depletion in the heavy isotopes. And then we have the so-called amount effect, and this is the same thing again. The more precipitation we have, stronger the depletion in heavy isotopes. Now, for a site like Jamaica, I think the most important will be this amount effect, because you don't have too much vapor transport over the continent, you don't have too much topography, but you do have a strong amount effect affecting the precipitation that is falling on an island. So you will have lower values with lower numbers with increased precipitation amount. Okay, and this is an exemplification of the values on the global scale. This is the delta D of the precipitation, deuterium, and here you can see the various types of effects that I was discussing. First, you see this so-called latitude effect. Here, closer to the equator, you have higher values. Further you move north or south, you have lower values. And then you have the continental effect, the source of precipitation in Eurasia. The main source is the Atlantic. As you move further inside, you have lower and lower values. Inside Asia, you have the lowest values. And then you can see the altitude effect here in the Tibetan Plateau. Higher altitude means lower values. And you can also nicely see it here in the Alps. And also here in the Andes, in the mountains, you have this altitude effect with high altitude resulting in lower values. So this is a summary of the processes that are shown in this cartoon here on a map. And then, yes, this is the highlight of the amount effect that is likely dominating in island areas because they are quite small and there is simply not enough time for the vapor once it leaves the surface of the ocean to travel and to see the altitude effect or the continental effect. Why does it change? Okay. Another important factor that is influencing the delta weighting of precipitation at a given site is the source of moisture, and this is the surface oceans, the delta weighting of the water, the surface of the oceans, and you can see that it follows the same pattern with higher values close to the equator, and as we go further north or south, you see lower values. Here you see the influence of the Gulf Stream in the North Atlantic with higher values. But I want to highlight this region here. So here is Jamaica. And importantly, depending on the source of the moisture, you will have different values. So if moisture is being picked up from this area, from the Caribbean Sea or the Atlantic, you will see that on average, the values are higher than if there is moisture coming from the Eastern Pacific Ocean. From this area, there is lower values. So regardless of these effects that I discussed before, an important factor in the value of the delta weighting value of precipitation is the source of the moisture. So you can have from here or from here different values. I'm based here. This is where I live. This is where I am now. So
one quick thing, sorry, Aurel.
Yes.
I was mistaken. Your cursor isn't visible, so unfortunately, we're not seeing where you're pointing to. I'm not sure.
Can you see it now?
No, we see the screen, but not your cursor, so I'm not sure.
So you cannot see my cursor now. I try to see how can I make it visible, because I'm trying to point with it. And so, did you see it before, or is it just you couldn't see it at all so far?
No, I couldn't see it at all. I confused my cursor for yours.
Okay.
Annotation
okay.
for sure.
Okay, let me. So I'm using Keynote. Let me try to. So just a short break. Let me. Okay, you still see my screen, I think. Let's see if I do it like this. So I will.
Maybe you can use annotations.
I don't know. Let's see if I open it in. I will open it in. Okay. I will open it in PowerPoint because I was using Keynote. So I will go back to this one. Okay, and let's see, I will share it again. Okay, can you see my screen now? Can you see my screen?
Yes, that's much better. We see the screen and the cursor.
Do you see the cursor now?
Yes, we're at our own Africa right side, back cursor. We're good.
Okay, it's mine. Okay, so I was presenting this. So I was talking about the delta weighting of the sea surface, and I was exemplifying with the position of Jamaica here and showing that depending on the source of the moisture, whether it is from the Caribbean Sea or it's from the Western Atlantic, Central Atlantic, it will have one value compared with moisture that will come from the Eastern Pacific having a different value. And even better, I was pointing to the area where I live and work here in Romania, and you can see that moisture is coming from the Mediterranean. From this trajectory, it also could come from the Black Sea, and you see the values are quite different. So it's very easy to differentiate between moisture that is coming from the Mediterranean or moisture that is coming from the Black Sea. And it's something like this. I know it's been attempted in Central America, in Costa Rica, with moisture traveling from the Atlantic or from the Mediterranean. So on top of the effects that I was showing before, and especially the amount effect, this source of moisture is also very important if one is to understand where is the precipitation coming from. Okay, so another way of looking at the delta, the stabilized composition of precipitation, is to look at the deuterium versus oxygen value. So the delta D against delta O18, and you can see most of the samples in precipitation on a global scale are plotting on a line, so-called the global meteoric water line, defined by this equation. There is a bit of refinement, but this is a good approximation of this equation. So you can see that almost all samples are plotting on this line. On a global scale, if we go into a more detail, then you will see a lot of small scale differences. And this is a summary of how this data in precipitation can be used to understand where is the moisture is coming from. So if you have on this scale, so this is from 0, you will see that precipitation on summer that will have higher values. Precipitation recorded in winter will have lower values. Again, this is the temperature effect, and you will see that low latitude, low altitude will have higher values. High latitude, high altitude, the effects that I was telling will have lower values. And then again, the lines could be shifted in this direction, indicating the change in the type in the source. These higher values above the global meteoric water line will indicate a vapor source that is more arid, whereas values below the global meteoric water line will indicate values that will indicate moisture that is coming from the humid source of the vapor. And again, you can have, if you measure on surface waters, lines that are not parallel to this one, but have a different slope, will show a loss due to evaporation. And depending on the slope of this line, you will have more arid or more humid conditions during this evaporation process. So the basic idea would be that if we collect stable isotopes in precipitation for 2 or 3 years, and we plot them on a delta H, delta 2H versus delta O18, we can understand partly at least the source and the travel path of that moisture. Okay, I will leave this here and I will come back to this image a bit later after I will be talking about the Karst hydrology. So we got the stable isotopes in precipitation, and then because we're in a karst area and then we want to measure the stable isotopes in karst waters to compare with precipitation. But first, a few words about the karst hydrology. So it will be a very general introduction to it. I will just put this about the karst system. So we have surface features that are sending the water underground. And importantly is the fact that the waters in karst, they do not behave as they do in the surface. So contrary to the first models of groundwater developed by Grund, actually, he was discussing about the karst water that was extending all the way below the surface, similar to the normal aquifer, whereas later it was shown that there is no such thing as a continuous groundwater in karst at the same level. So because we have caves and we have conduits and we have preferential flow direction, there is a strong difference, even in very short distances, between the depth of the water table. And basically we have several water tables at different depths that are present in the same karst area. And this is because, contrary to the normal permeability of rocks, we have the so-called matrix permeability, which is in normal rocks, in normal porous media, we have only this kind of permeability, which is given by the normal pores that we find within the rock. In karst areas, we have two more types of permeability, which are part of the same family, and this is the fracture and the conduit permeability, where the difference between fracture and conduit is only the size of those fractures and conduits. The fracture is just the joints and the bedding planes that are directing the water, whereas conduits are the same joints and bedding planes or primary porosity voids that were connected to conduits in which water can flow both under phreatic or free flow. So we have, this is important because this is directing the water to preferential flow lines, leaving some important parts of the underground devoided of water, and the water is concentrated in several points. And here is just an example. It's pictured by Christos Penos, who was talking today. So it shows this river here. This is the conduit permeability. So this is the entire conduit along which the water is flowing. And I put these just to show these stalactites, which are indicated areas where water is flowing along fractures, small fractures that water is coming enriched in bicarbonate and is precipitating it, depositing the spiratum. So these are fractures on the ceiling, and these are both this secondary type of porosity, and you cannot see the primary, but it's there in the rocks. The main issue with this kind of flow is that depending on the fracture frequency and the type of rock, you will have different types of organization of the flow underground. So you will have to the left, under letter F, you will have only this small pores and unconnected fissures or fractures, whereas to the left, you will have the very well organized system where you have input and then water is flowing through the cave and you have an output. So this is this case here, the conduit permeability. You can have in between these two several intermediate phases. You have a karst system where you have some inputs like normal river going underground, and then they will organize in a network and you will have an organized outflow. Or you can have the same network of caves with organized outflow through a conduit, normal conduit karst, like karst cave passage, but you will not see actually where is the water coming from, because all this network is being fed by water that is dripping through mostly the matrix permeability or to some extent the fracture permeability, but without having a fixed point, entry point that we can see and measure and sample. We just realize that at some point there is organized flow coming out as a river. Important thing here, I think, is this travel time, which is higher here and is decreasing as we go to this kind. So here we have higher travel time and here we have lower travel time. So depending on the frequency of the fissures and how well the karst system is organized, you will have changes in the travel time of the river, increasing with a higher degree of organization of the underground system. Okay, I just, this is the same, I think I will skip this because it's the same kind of information. What I wanted to show here is that this flow of the water will, in the karst, we will have several different types of water tables. And this difference between the so-called low water table and the high water table can be up to several hundreds of meters, and it's very dynamic in time, depending on how large the conduits are. This can rise in a matter of hours from 0 to 300 or 400 meters. And this type of circulation, it's not only happening here at the surface, but it's also happening below the water table. And this is where we have the karstification. So we can have karstification below the water table, we can have it at the water table, and we can have it above the water table during periods of intermittent flow. And this type of flow has led to several problems with the type of speleogenesis, especially where caves are being formed. And this is important because depending on where the caves are being formed, we know how the water is being diverted from surface to the underground and how it flows on the underground and how it gets out from the underground. And then we can understand where is the water actually coming from and how can we use it for our normal human use. So there are two competing or partly competing or maybe not competing, but it's difficult. The jury is still out on what is happening. I would say that it's the same way of putting for the same problem from two different points. So quickly, this is the so-called four-state model developed by Ford and Evers, and then has been explained and published very well in the Ford and Williams book. And basically, it says that the karstification is strongly influenced by the frequency of type of fissures that we found in a rock. So you see a progression from this type of speleogenesis where we have fissures, low frequency, and the water is, sorry. So the water, how can I, okay. So the water will flow along these bedding planes to very deep. So this is the surface of the phreatic. This is a phreatic on the surface of the water table. Will flow, and speleogenesis will happen at great depths, sometimes several hundreds of meters, kilometers below the surface. And with increased frequency of the fissures, water will be slow. The flow will slowly be drawn towards the surface of towards the piezometric surface. And with an further increase in the fissure frequency, we will see the so-called water table cave, where these loops that are here high amplitude will be reduced to very, very small amplitude, and all the dissolution will happen along the water table. Now, maybe a different model is that is a so-called epiphreatic model that is saying that most of the dissolution is happening in the epiphreatic zone, where we have the change in the piezometric surface, and all the dissolution is happening between these two levels, the higher and the lower level. And as these are going down, also passages are being abandoned, and the entire speleogenetic level is slowly lowering. Now, some are considering these are being contradictory, some are considering as being complementary, and I would favor both, maybe, for this kind of fissure. Very likely this is what is happening, where we have a high frequency of fissures, and not only high frequency of fissures, but we also have a very high frequency of input points. Then we would have this kind of behavior. And this is, I think, important for the cockpit karst area. I will have to go back a bit, because the frequency of the input points is extremely large. And then there is, the speleogenesis is likely some happening at this kind of the surface of the water table, and very likely underneath this surface morphology, you would have passages and conduits extremely frequent and very well interconnected, that are creating sort of, not sure how to put it. I think the best word that I come up for it would be like an underground marsh zone, so that water will flow not only in one preferential direction, but it would flow sideways in every direction. And in this, resulting in a very, very low transit times of water from the input to the output. So if one is to measure the water at the edge of the karst plateau somewhere here, this will integrate water on all these areas, and it's basically very difficult to find this kind of, I think it's a combination of these two, where you would have several tens of hundreds of input points and maybe one or two outflows. So this would be one of the points to be studied, I think, within this project. Okay, and here I put the map, and you can see these are the springs around the karst plateau, and here is a huge unknown area with all these input points, and very likely this kind of circulation, very, very, very slow circulation, resulting in leading to water outflows around the karst area. So in order to understand what is actually happening, and so in order to understand where is the water coming from, which are the water sources that are feeding these springs here, we need to understand what is happening in the karst area. And then in order to understand what is happening, I divided this the information that we need in 3 different parts. Would be the source of precipitation water, the post-precipitation processes, and the karst processes. The source of precipitation, it's important for the long term, because if there is only one source of precipitation, like the Caribbean or the West Atlantic or any of them, then maybe it is a bit easier to deal with it. But in the case where we have at least 2 or 3 different sources, these could change. So on the long term, in terms of years, decades maybe, in response to climate changes, we can see a shift in the main climate patterns and the shift in the main atmospheric circulation patterns. So this would could lead to changes in the amount of water that is available and that is delivered by precipitation. So I put this here because it's important from my point of view to understand the links between the sources of moisture, the precipitation amount, and then we can say something like, I don't know, 60% of the water is coming from the Atlantic and is being delivered by this type of circulation, or is being influenced by a certain type of atmospheric circulation pattern, for instance, El Nino. And then if this is well understood, then it's easier to understand what will happen in the future, because some models should in a few years predict better than they're doing now future changes in these atmospheric circulation patterns. So they can predict I don't know, change 20% increase in the frequency of El Niños, or a 30% increase in the frequency of La Niñas. And if we know how much water is coming during El Nino events and how much is coming to the El Niña events, we can predict how much water we will have in the future. Second, the so-called post-precipitation processes. I will show it a few slides later on, because so we have the precipitation water, but what is important is that this precipitation does not get directly underground, or this precipitation is not directly delivered to the springs. It goes through the karst, and before going through the karst, it goes through the rock on the surface. So there are numerous processes that are happening on the surface of the karst. So it's important to understand what is happening with the water there before getting underground. And then this is the step 3, to understand what is happening with the water underground. Let me exemplify this. So I'm coming back to this one, and I will show. So let's start first. I will discuss the source of precipitation water. I will go to post-precipitation processes outside the karst area, and I will then go to the karst. So first, we have to understand where is the water coming from. And this can be done. So if we measure the stabilized of composition, we can plot it in a figure like this, and we can say how much water is coming from, how much water do we get in summer, how much in winter, how much is coming from arid vapor source or a humid vapor source. But in addition to this one, we can model the trajectories of every single precipitation event. And here I'm showing for a study area in Romania. So Europe is here, yes. And this is from 2013 to 2016. And this is the winter and spring and summer and autumn. And you can see that in winter, between 2013 and 2016, there are quite large differences. In 2013, 2014, most of the precipitation was locally recycled moisture, whereas in 2016 and 2015 and 16, we had mostly precipitation coming from the North Atlantic along these trajectories. Now, in spring, it's somehow more constant. We have a mixture of western and eastern circulation. Again, western and eastern. Here it's mostly eastern, again, western and eastern. Summer, it's changing. So we have from western, you see red indicates from the Mediterranean. And then here we have from the Atlantic. Again, Atlantic, here more from the Mediterranean. And then we have the autumn precipitation, which is coming from all directions. And this is because, for instance, in winter, there are several climatic patterns that are dominating. The most important ones are the North Atlantic Oscillation and the Siberian High. So very likely in 2013 and 2014, the Siberian High, which is an anticyclone over Western Russia, was stronger than usual. So precipitation was coming from Western Russia during periods with stronger than usual Siberian High. In 2015, 2016, most of the precipitation was coming from the Atlantic. These trajectories would suggest that we had a negative phase of the NAO being the North Atlantic Oscillation. And this is the difference in pressure between the Azores high here and the Icelandic low. And when this difference in pressure is very high, the westerlies are directed northwards. And it's wet in Northern Europe and it's dry in Southern Europe. When this difference in pressure is low, the westerlies are directed southwards, and this part of Europe is wet, and this part is dry. So if we do this for several years, and we see where the moisture is coming from, and then we know the delta Eutin of the value, and we know the trajectories, we can link the source of the moisture with circulation patterns. So we can say, okay, if the Siberian high is stronger, we will have mostly precipitation coming from the east. If the NAO is in negative phase, we will have precipitation coming from the Atlantic. And the next step would be to look at the future, the projected dynamics of these two atmospheric modes of variability, the North Atlantic Oscillation and the Siberian High. And models are suggesting that in future scenarios, the North Atlantic Oscillation will likely change to a more positive phase. That means that Southern Europe and Romania will get less precipitation in winter. And then we can link these studies, the ones that I studied here, and say, okay, when we have NAO, negative NAO, we get about 60–70% more precipitation than we get in these conditions. But if these are changing, that means that we will not get this kind of precipitation. So the aim here is to link these precipitation events to circulation patterns that can be modeled for future and then understand on the very long time scales. So I think of 20 to 50 years, how much water we will get and where that water will come from. Okay. So here, just a short example, again, going into the same kind of information. I will put it here on this color coded by season. So red indicates summer precipitation, blue is winter precipitation, orange, yellow, orange is autumn, and green is spring. And you can see this summer, yes, like here, and winter here, the lower values. And you can see that all are along the meteoric water line. The black line is the global meteoric water line. The blue one is the local meteoric water line. So global, the one that I showed, and local only for specific precipitation. So most of the water is derived from this region. And this is on, so I showed this for general patterns, and I want to move into small details. This is a study that was done in Costa Rica with the passage of a cyclone. This is the path of the cyclone. This is Costa Rica. And you see this sudden drop in the delta Eutin values from values of about 0 per mil to nearly -20 per mil. Now, this is a very clear, it is like using a tracer. So if one is to measure delta Eutin of precipitation and, for instance, measure the waters in the cave, this drop of about 20 per mil in delta Eutin of precipitation can be traced underground. And then the question comes, can we see it or can we not see it? Because if we see it, that means that we have a very fast response of the cave system to the outside influences. Whereas if we don't see it, that means that the waters are mixed in the epikarst, in the rock above the water, and then these small scale variability is being lost. And then again, further, if we do see it, that means that these hurricanes, they have a strong impact on the underground flow, whereas if we don't see the same kind of response underground, that means that whereas hurricanes can, wreak havoc on the surface, they might not influence the water sources that we are seeing in the springs at the edge of the karst area. So this is one of the types of studies that should be employed in order to see the role not only of the large-scale atmospheric circulation patterns like here on yearly or multi-year scales, but also on very short, abrupt time scales. And here is, I think, yes, one of the examples of measuring. It was done by CNIRIM in Arkansas. They were looking at the delta O18 stable, delta O18 and delta 2H of precipitation, soil water, spring water coming out of the karst and cave stream. And what it shows, so this is the global meteoric water line, and this is the local precipitation. And what is interesting to be seen is that, so blue is precipitation, monthly values. You can see that in winter, they are more concentrated. So they are most of them are along the meteoric water line, whereas in summer, they are more spread out. And if you remember this figure, that means that they are coming from different sources. The ones that are above are coming from an arid source. The ones that are below are coming from a humid source. Whereas in winter, they are all on the same plot. So summer is more different sources. And here trajectory modeling can help for every single precipitation event to say where is this coming from. What is interesting is that in the soil, the water in the soil is mirroring that in the precipitation, spread out values in summer and more concentrated in winter. What is interesting is the fact that the average value of precipitation is here, the blue square. You can see that the spring values, they did not calculate a value for the spring, but they seem to be shifted towards lower values than precipitation. I would interpret this as an indicator of the fact that springs, the karst springs that are coming out of the karst area, are mostly fed by winter precipitation. Now, the question would be, okay, what is then happening with summer precipitation? And the answer would be that summer precipitation does not contribute that much to these springs because the water is evaporated from the karst. So even if maybe it's more rain coming in summer, that rain will not feed the karst waters. So it could stay on the surface, it would evaporate, it would only partly reach the underground, and then they come out through the springs. And you can see that also the cave stream, they have the same value with the springs. So the streams, the rivers and the springs, they have same value, and they are below the average value of precipitation, indicating a preferential recharge of the karst system during winter, with summer precipitation contributing less. And then you can couple this kind of information with that which I showed previously, with the source of moisture, and then with the amount of precipitation that we have in different seasons. And this will tell you what type of atmospheric circulation is preferentially recharging your karst system and also is recharging your springs, the sources of water that you are targeting. And then just to support this, so I was telling about this probably preferential contribution of winter precipitation. This is from a site in Romania. We were monitoring precipitation and drip water. You see, this is the meteoric water line. You see the cave drip waters are all above the meteoric water line. And then we interpreted this here, these values. So you see, this is August. These values were measured in 2016. And you see here is the precipitation. The precipitation values are quite flat. So nothing is happening in terms of precipitation outside. But we do see this increase in the delta O18 values. So from minus 10 to 8, we see an increase to between minus 7 to 4. And this is, the problem is that, okay, what is this signal telling us? Because it's not coming from precipitation. But we do know that the drip waters in the cave are coming from precipitation, and yet something must have happened between the moment precipitation fell out of the sky, clouds, and the moment it got into the drips. And then we looked at the atmospheric circulation pattern in 2015 in the summer, and it was the it was one of the driest year on record. So I think 2015 was the driest year over the past 20 or 22 years, I think. So, and what this is telling us that we had this kind of circulation. You see mostly easterly circulation, blocking conditions over Europe, very dry, extremely dry, very low amounts of precipitation, but these drought conditions were not influencing the delta within of precipitation. However, once the precipitation fall on the ground, because of these very high temperatures and drought conditions, it was evaporating before reaching the cave. So the signal in the cave was influenced by what was happening in the epikarst between the moment precipitation arrived on the surface and the moment that water reached the cave. So that's why I was telling at the beginning of this section of my talk that apart from understanding what is happening in precipitation, it is important to understand what is happening in the interface between the atmosphere and the underground, on the surface of the karst. If we are to understand, then again, coming back here, where is this water in the springs coming from? So I think I'm mostly done, yes. This is, I think, is the final slide where, in addition to measure delta H and delta H2 in water, one can measure the carbon, because carbon isotopes will tell us something about the behavior of the water in the rock. And this is the water values. So you see, this is the delta C13 in the dissolved inorganic carbon versus the amount of dissolved inorganic carbon in the water. As you would expect, there is no DIC in the rainwater. This is the soil water, and this is the carbonate rock. And the values in the spring in orange, and in the river, cave river, and in the springs are somewhere between that of the rock and that of the soil, showing that the rock, the values, the final values are a combination of carbon coming from the rock and from the soil. And important in this case is the fact that these values do not change when we are measuring the storms in low flow, in empty circles, and during storms. So during storms, we have a rapid transit of the water through the system. We have the DIC lower because we have the larger amount of water compared to the normal low flow, but the values, the delta C13 values, are more or less the same. So that means that the time that is available for this solution is well below that of the time required by the water to flow. So there is within maybe minutes or hours that the solution values are getting to these values. And this complement this kind of information, telling us that regardless of how fast the water is flowing, we will have a higher amount of dissolved organic carbon here because the water will have more time to dissolve it. But this will not change the isotopic composition. It will change the amount of dissolved when we have slow flow because more time will be available, but it will not affect at all the isotopic composition of the remaining water. So I think I will have to move to what I call the several suggestions. I have two. First is we need monitoring. We need the data. So we need the stabilized stops in precipitation, stabilized stops in cave, drip, and river water. And it's important to emphasize that we need drip and river water because drip water will tell us what is happening in the epikarst, what is happening from the moment precipitation reached the surface and the moment the water reached the rivers, the underground rivers that are eventually coming out in the form of springs. So this is important to monitor because this is an intermediary step that will tell us what is actually happening in the epikarst. And then we have the river waters. And of course, we have the springs because these are the outflow of the system. And the second kind of data, we need the climate data, temperature, precipitation amount, and we have to use these to model the backward trajectories of the precipitation events to understand where is the precipitation coming from. And if we have this for several years, then we can be able to put this, to link the source of moisture with the main atmospheric patterns that are determining it. And then we need to monitor the cave processes and the cave hydrology. Importantly, the transfer times, the flow rates, and the speed of the flow during both low and high flow. And all these data are important because what we need is the mechanisms. We have to link all these processes and to understand what is happening here. So we have this point number 1, stabilized topsoil precipitation, that will tell us what is happening from the moment precipitation starts to form up to the moment it reaches the surface. And then I think usually these two steps, number 1 and number 3, are the ones that are being used. So we monitor stabilized topsoil precipitation, and then we monitor in the river water or the springs. But there is a suite of processes that are happening in the interface between the two. And these are the ones that are determining the final isotope composition of deep water and the amount of water that is getting to the cave. And these two are the ones that are actually feeding the Karst system and the springs that we want to understand and to use for our own purposes. So I think, yes, this is my final slide. I will leave it here. This is it. I'm done. Thank you.
Okay, thank you very much, Aurel. I guess we could stop sharing if that's the final slide. Are there any questions thus far based on the presentation? For a very interesting presentation indeed. If you have questions, you can put them in the chat or lift or raise your hand and ask, such as it is. Let's see if there's anything on YouTube as well. No questions? All right, I have at least one question. Having seen these and gone through, I mean, you made a suggestion that in terms of looking at the delta 13 for carbon in the dissolving organic carbon, how do you think that, what would be the best way or your recommendation for usage of these techniques for this particular project, given what we've discussed with the area thus far?
I'm not sure I know, but I think it should tell us. So combined with the amount of DIC, so it's not only the stabilized composition of DIC, but also the amount of DIC and maybe DOC as well. It should tell us something about the dissolution processes. And I was looking at the data that you provided me on the transit times of the water that is in the order of weeks and months. It seems that the water is staying underground for a very long time, and this is why I was telling about this underground marsh. So it seems that there is water getting in the underground, and then it's a very, very, very slow flow. Very likely the gradient is very slow between the input and the outflow. So I'm not sure exactly where the dissolution is happening. Is it happening between the surface and these underground passages, or is it happening along the passages? Is the water getting to the underground conduits fully saturated, or is it still getting some aggressivity after it? Maybe just some mixing corrosion happening there that will re-enhance the corrosion. I don't know, but I hope carbon isotopes will be able to tell this. Okay.
Natalie Ferguson asks a question. I would have to answer that one. She asks if there are any isotope studies done in the Rio Bueno Basin to date. And as I can say, as far as I know, none have been done. There's a paper of some isotope work that was done in the Martha Braid Basin back in the 80s by, I don't remember her name, but it was this lady, think she's in Texas or somewhere, but she did some isotope work for the Queen of Spain region in Trelawney, in the Martha Brae, but I am not aware of any isotope work that's been done in the Rio Bueno. One more question that I have Dr. Gordon Smith clarifies that Catherine Ellens did the work in Martha Brae. I knew that it was some work done in that region, but nothing in Rio Bueno. We have been doing, there's historical dye tracing and current dye tracing that's been done in the Rio Bueno Basin. And both the current and the historical tracing have shown where there's a relatively rapid connection between sinks in the inlier, notably Cave River and others on the inside, that comes out of the major rivers like at the Rio Bueno, at Darnock, and Laughlin's Great River, and that travel time is in the region of days to weeks, relatively quickly. But at the same time, there are springs that outcrop along the contact between the Montpelier and the limestone aquifer, and those have not shown any dye trace connection. So we're seeing that at least two different flow regimes there between the relatively quick flow of the sinks and the groundwater, slow groundwater that you're referring to. And we haven't even begun to talk about the wells that are in the region. So having heard that, I mean, I guess we're going to talk about it more when we're dealing with the actual project itself. But what would be your initial idea of that difference between the relatively quick flow of sinks and rising and then the different source for the groundwater springs?
My first guess would be that you have different conduits at different altitudes, but I cannot comment. This is just a wild guess. I mean, it's something like very null hypothesis or something like this that should be tested. I mean, we should come up with 2-3 different possible hypotheses. One being that we have conduits at different altitudes, or we have some deep circulation, although I'm not sure I can understand how can you have very deep circulation there.
Okay, I guess that's part of what that's part of what the project can indeed comment on. Dr. Debbie Gordon-Smith, could you give some comments if you can turn on your mic? Because I know you did some work, you said some nitrate isotope analysis in Discovery Bay. You could probably give a little comment and feedback on what you've done thus far in that region.
Thanks, Jared. Morning, everyone.
Morning.
Yeah, we've done some preliminary work, very preliminary work in the Discovery Bay region. Just so everybody's aware, I'm a lecturer at UE in chemistry, geochemistry, and we focus mainly on water quality studies. Myself and some collaborators from the UK, from Scotland actually, Edinburgh, we did some analyses on nitrogen isotopes in nitrates last year, was it? I think it was last year. Found so far essentially fertilizer-based, sort of natural fertilizer, not fertilizer, natural or septic manure sort of sources for nitrates, as we kind of expected anyway. But that was it was a one-off study. We looked at the groundwater above in the Discovery Bay area and seawater as well in the springs, the discharge of groundwater out offshore. Other than that, I have also done some work on radon and radium, again in the Discovery Bay area, focused mainly on discharge of groundwater to Discovery Bay. So we have data for radium and radon in the groundwaters in Discovery Bay and the springs as well offshore. So that's what we have done so far.
Okay, thank you very much for sharing that information. Olive Morris has asked if there's any isotope study in the Cabarito Basin that's in the western end of the island. Again, I'm not aware of any isotope studies being done there. Doesn't mean it hasn't been done, but I'm not aware of any done in that region. But we do hope to eventually, in the medium-term future, to be able to quantitatively assess all the basins in Jamaica in that regard to see what can be done to identify the water resources and the flow dynamics therein using this very cutting-edge technology. Are there any other questions, comments at this time? Going once, going twice. Well, I believe that would then conclude this particular presentation at this time. It's given us a very solid basis for going forward with the WRA study. For me personally, I believe that I've identified at least 5 different types of springs or water sources that can be analyzed for the stable isotope analysis. That includes the sinking springs that we've done with iTracing, where we have the known sinks. The known rises that come up that I mentioned were relatively quick in the travel time of days or weeks. The springs that didn't seem to show any connection with the injected springs coming up, and that the wells in terms of groundwater pumping wells like Minards and other wells in that region. And of course, the rainwater analysis. It was very interesting to consider that the different sources of precipitation should be considered. We say, yeah, all the rainfall in Jamaica is coming from the Caribbean Sea. But then if we consider what's been happening recently with the various hurricane events and hurricane influence precipitation, there could be that rainfall is not just from the Caribbean Sea, but could be from the Atlantic and elsewhere. So that will be something to cover indeed. And yeah, this project just became a lot more exciting. And we look forward to the support of everyone here who can contribute in whatever way to the project's success as we continue to look at the Rio Bueno Basin and quantifying the recharge benefits herein. Thank you again, Dr. Persoy. I must give acknowledgements and props to the International Atomic Energy Agency, Representative Oliver Craft, who is here on the platform right now, and he also came yesterday. I don't know if he'd like to, as IAEA representative, just give a comment at the end of these 2 webinars as we begin to wrap up at this part and continue. Sorry to put you on the spot. Oh, he's not online at the moment, unfortunately. But I do want to acknowledge his contributions and what he has been giving thus far. So thank you all very much. The presentation will be available on YouTube. If you search for Water Resources Authority on YouTube, you can subscribe. You will see both presentations from yesterday and today available. And all the research as we go will be uploaded and you'll be kept abreast as for such. So if there are no other comments or questions, I thank you all again for coming, and I wish you all a very wonderful day. Goodbye.
Thank you.
Thank you.
Thanks, Leon. Nice to see you again.
Yeah.
We'll be in touch.
Take care.
Definitely.